Today, we're doing something a little different. We're not just looking at some technical problem, we are diving into a genuine engineering detective story. I'm talking high stakes, some really unexpected twists, and a culprit that, believe it or not, was hiding in plain sight the whole time. So let's start the investigation. All right, so our story kicks off in the world of solid rocket motors. You know, SRMs. These are the absolute powerhouses, the boosters that help giants like the space shuttle literally defy gravity. And as you can probably guess, testing a full-scale motor like this is incredibly expensive and super risky. You really don't want to discover a tiny mistake when millions of pounds of propellant are about to go up in flames.
So to get around that, engineers do something really brilliant. They build miniature versions. And this is our main character, a super meticulously designed 1:31 scale model. Its entire job is to perfectly copy the internal ballistics of its much, much bigger sibling. This lets engineers predict performance and, iron out all the kinks before the real deal is ever even built.
So the team built 3 of these models for a series of static fire tests. The first one was just to get a baseline, and the next 2 were meant to kind of fine-tune the performance. They were expecting some pretty routine data collection. What they got instead was a mystery that threatened the entire project.
And here is the absolute heart of the mystery. If you look on the left, you see the pressure curve from the first test. See how it's smooth? It follows the prediction perfectly. A total success. But then you look to the right, and that's the data from the second and third tests. A catastrophic, almost instantaneous pressure spike that just ripped the motor apart. And they were identical. Violent failures. So what changed? I mean, the motors were supposed to be identical. What could possibly cause a perfectly good design to suddenly fail, not once, but twice in the exact same way? That's the big question for our engineering detectives.
All right, so the investigation kicks off. And just like any good detective story, the team started by rounding up all the usual suspects. They had to go through and systematically check every single component that could possibly maybe lead to this kind of crazy overpressure event.
So here's their list. Could the propellant chemistry be off? Maybe the igniter misfired? Was there some fundamental error in their calculations? Or was the cause something that no one had even thought to consider? Let's watch them knock these suspects down, one by one. First up, the propellant. But here's the first real twist in the case. The propellant they used in the failed second and third tests was actually a less energetic, more moderate formula. It was specifically chosen to lower the peak pressure. So if anything, this should have made the motor safer, not cause it to explode. The propellant was definitely innocent.
Okay, next up, the igniter. Maybe it gave too powerful of a kick at the start? Nope. Just like the propellant, the igniter charge for the second and third tests had also been reduced. The whole idea was to give it a gentler start. So no way the igniter could be the cause. Another suspect cleared.
So what about the design itself? Maybe a fatal flaw in the math somewhere? Well, this got rolled out pretty fast, too. The evidence was simple. The first test worked perfectly. It followed all the ballistic predictions to a T. The blueprint was not the problem.
So, with all the usual suspects cleared, the investigators were left with really only one possibility. Whatever was happening after ignition. The nozzle must have been blocked, or as engineers say, choked. The physics here is actually pretty simple. Just think of a rocket motor like a pressure cooker. The nozzle, or the throat, is the little valve that lets all the hot gases escape, and that's what generates thrust. If that valve is open, the pressure stays stable. But if you suddenly block that opening, well, the gas has nowhere to go, and the pressure builds with terrifying speed until the whole thing just blows. So the team ran some computer simulations to test this theory. On the left, you can see the gas pressure with the normal 45mm throat. But on the right, that's what happens if the throat suddenly shrinks down to just 20mm. The internal pressure just skyrockets, and it perfectly matched the conditions of the explosion. And this number, it's just staggering. 225 bar. That's the pressure spike that was measured in the second test. We're talking over 3,000 pounds per square inch, appearing in just milliseconds. The motor casing was only designed to handle about 80 bar. It never stood a chance. So at this point, the team knew what had happened. The nozzle got choked. But they still didn't know why. And the answer, it turns out, wasn't some complex failure of materials or some deep design flaw. It was something almost deceptively simple. The culprit was a simple assembly error. When they finally inspected the wreckage, they found that the throat insert, which is a separate part that's fitted into the nozzle,
had come loose and had actually fallen into the motor, creating the exact blockage that their simulations predicted. So here's how it all went down in just a fraction of a second. The igniter fires, and that creates a shock wave. This wave travels to the back end of the motor and then reflects forward. Because that throat part wasn't secured properly, this returning pressure wave just popped it loose. The dislodged part instantly blocked the nozzle, pressure went through the roof, and the motor blew apart. And all of this happened in about 40 milliseconds.
And this is exactly where it failed every single time. The pressure wave created by that blockage didn't build up evenly. It just slammed into the flange connection between the first and second segments, which became the weakest point under that huge, sudden force. The evidence was a perfect match.
But why wasn't it secured properly? Well, the research paper states it plainly. For the first successful test, the operator had roughened the metal surface of the nozzle before applying the adhesive, which created a really strong bond. But in the second and third tests, this simple but obviously crucial step was missed. The smooth surface just couldn't hold, and the shock of ignition was enough to break the part free.
So, case closed. But the story really doesn't end there. Because this single failure teaches a really profound lesson that applies to pretty much any complex engineering system that we build. This was not an isolated incident, not by a long shot. In fact, the researchers point out in the introduction to their paper that somewhere between 80 and 90% of all failures in complex systems like this, they aren't due to bad design or material defects. They're due to human factors. And that, right there, is the ultimate takeaway. A sophisticated, expensive, powerful piece of hardware was just completely destroyed. Not by a failure of physics, but by a failure to properly apply some glue. In this line of work, every single detail, no matter how tiny it seems, is absolutely critical.
And that kind of leaves us with a final thought to chew on. As our technology gets more and more powerful, more and more complex, have we maybe reached a point where the most unpredictable and maybe the most critical component in the entire system is the person holding the screwdriver? Or in this case, the adhesive?